This is the third in a series of companion videos for the QuickStart guide for Ceph environments. We've moved on to another system that has a fairly full catalog. There are 21.5 million files spread across some 50,000 volume sets. And the first thing we notice here is we have a flashing warning light, so just check that. There are a number of things that we monitor to try and give the operator a heads up when there are things that need attention. So in this case, we're using almost 90% of the scratch volumes that were initially added to the system. So it's just telling us that of the initial load, there's only 11,500 out of 96,000 left. So that's fine. The next thing you're probably wondering, if you watch the process for creating volume sets that I outlined in the second video, it was a very manual process, and you might be wondering how on earth I got 50,000 plus volume sets. So the answer is that we, in this case, use a data management policy that created the volume sets automatically based on characteristics of the files that were being ingested. So let me talk about this process a little bit. And first of all, I want to say that this is not a live production system. It's a simulation that was done for a prospective customer. So the user IDs and the file names are contrivances that were part of the simulation. The TIFF image files are not, well, they are TIFF image files, but they're just basic rubbish that I scanned from my office files. So there's nothing sensitive in this demo. We're going to take a look first at the structure of the volume sets, and I'll talk about how we went about creating them based on the records that were ingested during the process of this simulation. So as you can see, the volume sets are each numbered with a user ID in this case, followed by the generation and version syntax that we discussed again in the second video. So when I check on any one of these, I would be looking into an individual user's folder simulation with their file simulated file data. So we look at the file listing, and we have all these forms that are saved as images, and they're all associated with that particular user ID. And they got here through a data management policy that created the volume set with that identifier string, and then routed all the files as they were ingested into that volume set. So let's take a look at the policy that was responsible for that. So what we've done is, as I discussed in the second video, we create volume sets, we create file filters, and then we create policies that associate one or more file systems with that filter and that volume set. So in this case, we have a number of file systems. So the architecture of this particular application was designed to distribute in a round-robin fashion all of the user records that came into the system across a large number of file systems, so that no one file system would have to scale to hundreds of millions or billions of files. So our simulation put a data management policy on a large number of file systems. It's a one policy where the file filter looks for this particular regular expression string. And that string starts with the word image, which is a top level directory below the mount point, followed by a dot, which matches any character, in this case, the backslash, which is part of the directory structure. Then it would match a subdirectory underneath image that is constituted only by integers, followed by another dot that represents the next backslash, getting into the subdirectory below that, that matches just another string of integers. The target volume set then has the typical root ownership, But the DYN is a keyword meaning create the name dynamically with the back references that follow. So inside the braces, the first back reference is the second string, and the second back reference is the first string. So we can do up to 10 of these captures to compose the volume set name. So if we look at what that looks like in the file system space, so this would be a typical target directory. It's got one of those mount points. Top level directory under that is named image. The directory under that is a string of integers, and the directory under that is a string of integers, and then there's a handful of files. So the way this works is, as the files land in the directory, no matter what file system that directory's in, the determination will be made what volume set to route the file to based on that component of the path. And if the volume set does not already exist, it'll be created. And if it does exist, it'll be reused over and over again as more files are appended to it, as they're written to any one of these file systems using this particular mount point or this particular path relative to any arbitrary mount point among the pool of managed file systems. So that's the way that particular policy works for a particular application with a very specific type of data set that needed to meet very large scale requirements, and where there was a desire to curate the files based on individual user IDs and events in that user's career, beginning with them joining the organization to leaving the organization to all the events in between those two endpoints, so that the people responsible for these records could then manage them appropriately based on chronological criteria. And when the time came, those records could be transferred to an offsite cold vault on a per user basis. So now let's talk about some of the capabilities. Before we do that, let me talk about another data management policy that's more applicable in a broader scope. Let's take a office automation environment. Let's say that, for example, I want to create a volume set based on a type of file based on a type of application. So let's take an instance where, say, the user base is, say, dealing with CAD documents, and they might be using multiple types of CAD application software, or they might be producing videos, and depending on who's doing what stage in production of the video or post-processing the video, there will be different applications saving files with different extensions. So what we want to do is, in either one of those cases, we want to group files minimally based on the type of application. So that is a good use for what we call extension templates. So let me take an example extension template, which I've already created for multimedia files. And I just named this extension template movies, and I've already put 8 different extensions in here. Now, if I'm a storage operator and I don't know a lot about the applications that my users are using, I could quite easily be excused for not knowing what extensions a particular application would use. So we created this extension lookup, and this button won't work unless you've populated the extensions table with a file that's available on our forum. It's the extensions.sql file. But if we select this and we select a category for, say, movies and multimedia, we'll come up with a scrollable list, and we can check off any applications that we recognize that our users might be using. So let's just grab this one for the sake of demonstration. We save and close, and we added that extension. I can also delete it. But what we do is we go through and just add all the different extensions until we've covered all the bases in terms of what our users might be using for their applications for this typical classification of data. And once we've done that, we'll go back to file filters here. And what I've done, this is a template regex type of filter. You can see I selected the name movies with the extension template of movies, but I associated it with my user ID. Now, I could have associated it with any and group any. That would aggregate all multimedia files into this one volume set. But it's more likely I would want to route my movies into my individual volume set, or I might want to do it based on a group, okay? So then what I've done is I've associated that, that particular policy with a particular file system on a host, and I've associated it with target movies. I probably should have made that SCRAN Edge movies, but you get the idea. Okay, so now let's go back to some of the other features. So since we populate a file system database, obviously one of the things that we want to be able to do is search. So let's take a look at the file search tab under the file system main tab. And we go back and just grab a portion of one of these files. So I'm going to put that in here. So we'll look for any file name that begins with that 312SF. And I'm not going to restrict my search. It will be across any host, any file system, any owner, any group, and with a creation of any time. Now, obviously, if I were to do this with normal find, I'd have to run it on every individual file system. And in this case, I'd have to drag 21.5 million files or their file inodes through system memory. So in this case, we've translated that particular capability into a database search, which has a near immediate response as opposed to the file command, which would take probably hours. So that's just one of the ways in which we try and make the operator's life a little bit easier. Let's move on to version rollback as the next capability I want to demonstrate. So let's say, for example, I had an instance a while back where I went through an excruciating configuration of an LDAP server, which I'd never done before. And when you configure LDAP, there's an awful lot of files that have to be configured. There's certificates, there's configuration files. Most everything lives under the etc directory. So let's just say that I wanted to, at the culmination of this process, I wanted to go through and find all the files that I had changed. And maybe I even wanted to roll back some of those to a prior state because I fiddled the system to the point where I couldn't even authenticate. So I might choose a path like etc in that case, but since I've already got a file name string in the buffer, I'm going to use that. And I'm going to say, look across all hosts, all file systems, and let's just take a look at everything from last summer to today. And what this will do is give me a search on all the files that match that string on any host and any file system, any owner, any group created during that, I don't know, 5-month window of time. So this is going to come back with obviously a very long list of candidate files that match that string beginning. And I could pick any one of these then, and it would show me all the generations that exist. So in this case, I picked one obviously that only has a single generation. But if this file had been modified, there would be a list of generations and I could roll back to any one of them. So in the situation like I just talked about, where I had spent an entire day futzing with a system, messing with a whole bunch of configuration files, this would allow me to backtrack and find every single one of those files I touched and roll them back to any generation that I want, with a demonstration here of when they were created, when they were last accessed, et cetera, et cetera. Okay, so that's version rollback. So that's, if you watched my second video, you saw me demonstrate the rewind command. So this is sort of the same effect, but it's the next step up in terms of functionality that's added by the graphical user interface. Next, we'll talk about the baseline. So I talked about the record management system before. That customer had actually been operating the system for a couple of decades. So they had hundreds of millions of files that were already ingested into pre-existing file systems. So since our framework is based on events, you might wonder, well, how do we ingest files into the system without having to rewrite them all after we build a new managed file system? A solution to that problem is very simple, is choose a host, and then we can select any of the file systems that are managed. Well, they have to now have a management policy applied to them. So I can take an existing file system, I add it as I did through video to this configuration, I add the policy to it, and then I can check off any or all of them to be baselined. And when I press the create button, what happens is a file system crawler, multi-threaded file system crawler, is launched on each of these file systems in parallel, and it stats every file and puts every file's metadata into the primary work queue that's associated with this file system, or each one of these file systems. Then the policy that is now in place on that file system will see those files, and we'll see them in the same fashion as if they had gone through the event management system. So they will be added and they will be archived as generation 0. Obviously, we can't do anything about the generations that were written prior to the application of data management policy, but going forward, any file changes that occur in any of these file systems then become part of the version management system. So that is the mechanism for taking your data management policies, ingesting pre-populated file systems, and starting afresh with new data management on old data. Point-in-time recovery is the next thing we're going to talk about briefly. This is very important in the context of a ransomware attack. So let's go back to our managed file system. And let's just do a copy of the etc host file atop one of these records for the purposes of corrupting it. And yes, I'm going to overwrite. So now I have taken a record and I have corrupted it by overwriting it, which is obviously something that happens quite often in an operational environment. Or it could also happen by malice through a ransomware attack. But assume that this had been a ransomware attack and the overwrite had occurred across millions of files and dozens of file systems and hosts. What we want to do to unwind that damage is simply come into this point-in-time recovery screen, pick a host, pick a file system. In this case, it's RMS1, and we want to select a time frame. Okay. If you remember, in the find screen, I could look at files that changed during a period of time. So let's say I come into the office one morning and I realize I've been the victim of a ransomware attack. The first thing I'm going to do is do that find command, but instead of giving it any kind of a string to look for, I'm just going to give it a time window. I know the ransomware attack started sometime after I left the office, and all I want to do is make sure that the beginning of that file search time window is just prior to that time. Then I'll see all the files that were changed. All I have to do is grab the one at the top of the list, get the time, and that I know was the beginning of the ransomware attack. So I could enter the calendar date and time to match that, or I could just go back and say, you know, it was an hour ago that the attack started. So then we'll go ahead and do the restore to file system, host, original file system, run the recovery, and at this point, it will look across the entire catalog to find out what files had a change in this time following 1 hour ago. So you'll see it identified the one candidate file. In a ransomware attack, obviously, this might have been millions of files. But what it had to do was not move data to restore each file individually. That would have taken a very long time. All it had to do was find out which files were affected. Then it went in and purged the resident copy of the file, which is corrupted, and reorder the LCR extended attributes so that the one that is in effect is the one prior to the beginning of the attack. So it gets through this process very quickly, and it rewinds all the files that were subject to the attack, leaves them in a purge state so that the next time the operator accesses that file, it gets brought back from the catalog in a pre-attack generation. So very quick and easy way to unwind a ransomware attack, and probably something that will make you breathe a huge sigh of relief if you ever find yourself in that circumstance. Now, finally, I want to discuss this file system synthesize capability. Then I'm going to go into an architectural discussion to explain why this capability is here in terms of our ConOp and the way we intend to achieve a scalable namespace while still maintaining a file system user experience. So the idea of a file system synthesize is, so we have a database that has all of our file metadata, and we have a catalog service namespace that has all of our files version controlled. The idea is the catalog is the global namespace, and we don't want to deal with it directly because it does not have an interactive user interface. It's designed to basically be a batch processing type of namespace for the purposes of scalability. So it has very coarse grain locking, which I'll get into shortly. And it has very few modalities. It just doesn't support the kind of operations a file system does. So what we want to do is shield the user from having to deal with a catalog by being able to virtualize a file system any place, anywhere, anytime that is pre-populated with files from that catalog based on a database query. So the purpose of this form is to, create a very simplified interface so I don't have to type in the SQL query. It's just filled in by the elements that I put into this form. So in this case, I'm going to choose a source file system that has 1,000 3.5 gigabyte videos. And I'm going to tell it to clone that file system or synthesize it to another file system. And before I do this, I'm going to cd there, and I'm going to do an rm dash or star, wipe everything out so there's nothing in that file system. And I'm going to specify a owner and group and mode for the directories in that synthesized file system. And I'm going to hit the create button. And now you can see I have all of those videos, 1,001 of them, which I can play from this particular file system. So that's 3.5 terabytes of data that was copied into this file system in a virtual sense, because it's a metadata only operation. These are just stubs. If I look at any one of them, it's only 4K in size. But if I do an mPlayer on it, it will play on this and restage the file to facilitate that play. So basically what happens here is there is a database query that comes back with a candidate list of files. That database query is fed into a utility that we created called DS-Touch. The DS-Touch finds all the files in the file system database that match the query and touch the file, creating a stub, set the regular file system attributes, and then more importantly, create the LCR that allows us to restore that file to this location when it's opened. So with that, I'm going to pause and move on to a PowerPoint to try and describe the intended purposes of the DeepSpace SMS architecture and why it's built the way that it is.